All right, ladies and gentlemen, so let's get started with thermochemistry. This is about heat and specific heat, or Q and CP. So let's get into it. So when we're talking about thermochemistry, we have a few different perspectives we can take. In this section, we're going to talk about Q and CP in solidarity. We will add in more layers as we go through the unit. But some fun tits and bits and things to remember. This tiddly bit of information right here is very useful knowledge to know. Water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. So make sure we remember those little fun facts of everyday knowledge. So when we're talking about heat, we're talking about thermal energy, also known as heat, in terms of joules. Joules is always the unit associated with Q. Always. But generally talking about, we understand heat as we perceive it. And us as mere humans perceive heat as temperature. That's not 100% accurate, however. Temperature is a direct correlation to particle movement. So what we mean when we say there's high temperature, what we're really talking about is that high movement of particles. And vice versa, when it's cold, you have less movement, but the particles aren't moving around as much. But temperature is not a direct measure of heat. Temperature is not a direct measure of heat. What temperature is doing is telling us the measure of kinetics, or that motion of particles we have, whether we're talking about more collisions with high temperature or less collisions with lower temperatures. And we can see that when we're talking about our states. When we have a solid, things that are solid tend to be cooler than things that are at gases. Because in a solid arrangement, the particles are moving around in place. They don't move very far, so they have low movement, so therefore less collisions. As we add in energy, heat per se, things start to get some more space. They start to get room to breathe a little bit. Then we move into what's called a liquid, where things can ebb and flow and bend around each other. Add some more heat and we got gas. Gases are always in constant motion, whipping and zipping and diving around, always moving, that have higher momentums relative to their energy levels. Now, what happens if I start taking this fire or this energy away? I start removing some of this energy. I remove some of this energy. I go back down in transitions, right? So that's when we get this thing called a phase change diagram. That's what this graph right here is called, if we remember. It's a phase change diagram. And we can talk about it in a few different perspectives as we're going up the ladder. I'm increasing in energy following that blue line. I'm going up in energy. Let me get a consistent little pointer here. I'm going up in energy as I move from a solid here to a gas. Or I can move from a gas down to a liquid, down to a solid as I decrease the amount of energy in my system. So whether I'm moving energy, that is what we're talking about with this thermochemistry. We're tracking the movement of this heat. We're tracking where it goes and what it does. So in these cases, the thermal energy is used to separate the particles from each other, giving it space. That's what's happening here and here. That's the reason it's a plateau. The reason we see a plateau here and here is the temperature is still increasing and the energy is still increasing. However, they're doing different jobs. From this point to that point, roughly, we're heating a solid. We're putting energy into the system, into my solid, and the particles are starting to vibrate, then increase in vibration and increase in motion and increase in kinetics. Once they reach a threshold here, we start to not just want to start shaking more or moving more in place. Now we are actively separating out. We are putting more distance between our neighbor. We are melting, moving from a solid to a liquid. Then the same idea applies at a liquid. Here, I'm a liquid. I'm just liquid water sloshing around in your water bottle. But if I increase my temperature, making my energy go up more, I move further down my graph here. I move up on my liquid state, and then I reach my threshold here. Right here, where we're talking about vaporizing or evaporating, I'm getting more energy to separate these particles from each other more so, letting them move more freely, turning them in from a liquid into a gas. That is what a phase change is doing. And this part of thermochemistry is doing the math behind those phase changes so we can calculate with certainty what's happening. And each of these substances that undergo this phase change has a specific threshold that happens as we move from there to there and there to there and there to there to there. There's specific amounts of energy that need to happen. And that specific amount is called a specific heat, or C sub P, a specific heat or heat capacity. When we're talking about heat capacity, it's very, very unique to each substance. It's highly individualized, down to the state at which it's in. A solid will have a different specific heat than its liquid. A liquid will have a different specific heat than its gas version. So solid water has a different specific heat than liquid water, than gaseous water. They're highly specialized. They are very, very specific. And the good thing about these, however, is these tend to be constant values we can use to do math. If we're not asked about it, we assume it's a constant value or a pure substance, then we can use that data from our reference sheet to do some math. And its unit is very unique in itself. It's a derived unit talking about joules per gram degrees Celsius. So when we're talking about specific heat, if we're talking about how much energy it takes to heat it by specific heat, that's just joules. If we're talking about specific heat as a independent item, that's our unit right there. And it's the amount of energy it takes to raise 1 gram of substance by 1 degree Celsius. So how much would it take to move it from here to here? Capiche? 1 gram of whatever substance this graph represents by 1 degree Celsius. And that information helps us extrapolate out further how long something takes to boil, how long it takes to melt, how stable this compound is, how can it resist change, all those kind of information. And we have 2 flavors of calculations. I can ask you about heating a substance or heating a phase change. Heating a substance is a whole picture of what's happening to my substance. Of a phase change, however, is individualized to a phase change. So as we're moving through our graph here, this is a state, that's a state, that's a state, one of our 3 main states we have here on Earth. But these places right here, I'm gonna highlight in yellow, have unique names. These are called my phase changes. It's where things are actively turning from one thing to the other. Our phase change information has not gone anywhere. I could have been a better rectangle here. Oh my goodness. This is why I'm a scientist, not an artist, y'all. Bear with me. All right. So those spots are where we have an active phase change. And we're talking about whether it's a phase change of a gas or phase change of a solid. Phase change of a solid is called heat of fusion. So if I'm talking about heat of fusion, I'm talking about a solid either melting or freezing. That's the same process, just from different perspectives. Is energy coming in or energy going out? That is heat of fusion right here. And moving over back to our little spot here, we have heat of fusion and we have heat of vaporization. Heat of vaporization is the energy it takes for a phase change to go from a liquid to a gas. That is called heat of vaporization. And that differential is notated up here. Right here is called heat of vaporization. So vaporization makes vapors. It's another way you can remember it. But if you're talking about heat of vaporization, you are currently politely sitting right here. That is heat of vaporization. So those are two fun facts you have to recall from our previous units. And these are constant values. They're constant values that we see on our reference sheet. When we're asked for the Q of a phase change, you have to be able to recognize the phase change trigger words. I'm melting, I'm freezing, I'm boiling, I'm evaporating. Those are phase change trigger words that we need to know to talk about these situations here. Most importantly, right there. Those are our constants we're going to use to fill in this variable right there. Or we can do the whole kit and caboodle where we're talking about heating a substance, getting the bigger picture when we're talking about this situation right here, where Q equals mc sub p delta T, where this m is a mass, and this C sub P, of course, is that specific heat we just talked about. And delta T is a change in temperature. That's what delta, that triangle right there, means, change in. And to calculate delta T, it's TF minus TI, or temperature final minus temperature initial. That will get you your delta T. And it's quite possible you have a negative number here. It's quite possible. It just tells you the direction or the directionality of your energy flow. If it's coming in, it's going out. So let's see what happens when we put this information to use. So let's try this first problem here. When a sample of KCl dissolves in 335 grams of water, the temperature drops from 51.0 degrees Celsius to 35.6 degrees Celsius. I'm asked to calculate Q. All right, well, I know two things. One, I know I'm asked to calculate Q, so Q and Q. All right, cool. And the next thing, a sample of KCl is dissolving, okay, and that much water with that kind of differential in temperature. Okay, ain't nothing in this situation talking about a state change. So I can go ahead and knock out those options because no state change was mentioned. Here. Right? There's no trigger words that mean a state change. Melting, freezing, boiling, anything like that. So, I'm going to dive in with that one. So, as a good scientist, I'm going to bring down my formula. Q equals m C sub P delta T. That's what Q equals. So now I look at my equation and start to fill in some dots. So I'm asked for a sample of KCl, but in reality, I don't know a lot about this, besides the fact that it's dissolving. And the only thing I can glean from it dissolving is it's likely dissolving in a liquid. And it tells me that much about it being dissolved in a liquid because it says I have that much water. Okay, so let's keep it pushing. So I don't know nothing about the KCl, so I keep pushing in 335 grams. Grams is a mass value of water. The temperature drops from 51 degrees Celsius to 35.6. So since I don't know enough about my KCl, besides the fact that it's dissolving, I'm gonna run with what I know. I have 335 grams of water, and it's likely liquid water, so I pull up my handy dandy reference sheet here and scroll on to the back where it talks about these thermodynamic constants. In these thermodynamic constants, I'm going to find the specific heat. So that is just your reference sheet I have pulled up here. And now let's splice out what we need. I'm going to take the specific heat of liquid water because I'm dissolving in a liquid. So I'm going to use the specific heat for a liquid. So it matters what state you're in because specific heat is specific down to the state. Joules per gram degrees Celsius. I'm throwing in these units so you can see where they're coming from and what they represent. And I get a temperature change. I start from 51.0 and I go to 35.6. So if I'm starting from somewhere, that's a TI or an initial temperature. And then I'm talking about TF or a final temperature. And I know it's TF minus TI is delta T. That's that delta T moment right there. And you should be starting to realize something unique's about to happen. Something unique is going to happen here. So if I want to just focus on isolating what this value will be, I'm going to plug it in my calculator so we can see. 35.6 minus 51.0. That gets me a negative 15.4 degrees Celsius equals delta T. Why do you think it's negative? Well, one, I see it dropping, going from 51 down to 35.6. So I know my temperature's going down because my energy has to go somewhere. Where my energy is going is into this KCl substance. It's going in there to ionize this KCl. What's happening is why it's going low is KCl is a solid, right? So my energy has to go into my solid to help disperse it. It's helping to get dispersed or dissolved, or i.e. ionize this ionic compound. That's why we take so much energy out. So then I know why it's negative, so I should expect a negative answer. So we just go run some math. And in the regular classroom calculators, you can do the exact same thing I'm about to do. You just have to do it stepwise. So go ahead and find your delta T like I just did. And then plug and chug everything together. And just like that, we have an answer. Where Q is equal to that negative 2156.4.62. 0.62 what? What's my unit? Q is measured in joules. There's also one extra problem here that we should be jumping up and down by now. is your sig figs. How many sig figs should you be reporting to me? So let's see here. I see 3 sig figs from here. I see 3 from here because that 0 plays a role. And I see 3 sig figs from here. Well, if I got 3 sig figs all the way around, I should be reporting in 3 sig figs. So let's put this how it's supposed to be. I see 1 sig fig, 2 sig fig, 3 sig fig. Well, that one's going to play a role into that one. So we're going to do some rounding. So Q is approximately negative 21.6. Everything else is a 0. All right. And your final answer is 21,600 joules, or negative 21,600 joules, because my energy is lost moving from my water to my KCl compound in order to break it down. So I encourage you to pause the video and try this one out on your own so we can check our answers. I'll give you a second, and let's get into it. Now be honest. Which one are we doing here? I have a 15.2 gram sample dissolves at 95 grams in 95 grams of water. The temperature changes from 33.4 to 41.8 degrees Celsius. Calculate heat, or in other words, I'm looking for Q, because Q is heat. I ain't got nothing to do with a phase change in here, so I know I'm going to do that Q equals mCp delta T. But besides, I have a mass. I have a mass here of a sample that dissolves. I know from experience, dissolving is likely happening in a liquid. But besides this mass right here, do I know anything else about it? No. But I do know lots of stuff about this 95 grams of water pulling from my reference sheet. So I'm going to run with what I know. So I'm pulling in that 95 from what I know about water times C sub P, or that specific heat. Well, if I'm dissolving, I'm in liquid water here. That's going to be 4.18 joules per gram degrees Celsius, and this is in grams, y'all. And here we go. I'm talking about from 33.4 degrees to 41.8 degrees. So my initial temperature is that. My final temperature is that. That tells me I'm heating a substance because I'm going from a lower temperature to a higher temperature. So I'd expect a positive answer here. So TF minus TI would get me that answer. And here we go. Now that I have all my bits and bobs, or tits for tats, or whatever acronym you want to use, go forth and prosper. Plug and chug what you want to know. Plug and chug what you want to know. I want to know heat, so I'm going to plug in all my parts and pieces for heat. I get 33,335. Ooh. 3,335. Ooh, Jesus. 0.64 joules. All right, cool, groovy. That's an answer. That is indeed a answer. However, comma, I see 2 sig figs. I see 3 sig. I see 3 sig figs. I see 3 sig figs. I see 3 sig figs. 3 sig figs. 3 sig figs. I'm gonna go with I need to be in 3 sig figs. So here goes 1, 2, 3 sig figs. That one does what to that? 3. You got it, round it up. So here we go. I should have an approximation of Q to be 3,340 joules. To be the best answer I give, and I always want to give my best. So that's how we do that one. And again, before we get too deep, this value right here is a reference sheet constant. It's a reference sheet constant. For liquid water. Now let's try another one. How much heat is it required to increase the temperature of 31.5 grams of steam from 101 degrees Celsius to 107 degrees Celsius? So I'm actively heating steam here. I'll give you a second to think about it. Pause the video and try it on your own. And let's get into it. I see a trigger word. I see a state. I see a state. Anytime I see a state, I know I might have to use a different CP value or a different specific heat. So I got to pay attention to what's given to me. So how much heat is required to increase the temperature? So I'm increasing the temperature of a substance. So that is, off the jump, Q equals mCp delta T. Now let's plug and chug what we know. I'm going from 101 degrees Celsius. That sounds like an initial temperature to me. Then I'm moving to 107. That's my final goal. Now let's plug and chug. I have 31.5 grams of steam. So I'm going to pull my reference sheet out. I'm going to look for steam. Ooh. I see steam right here. So, if you see steam, use steam. That way, we all can be using the same units, and all the math works out just fine, because that is what you're supposed to do. The goal is to make the math. So here we got that 2.02 joules per gram degrees Celsius here. And TF minus TI, all of that equals Q. So let's plug and chug into our lovely handy dandy calculator. 31.5 times 2.02 times 107 minus 101. That will give me a Q value equal to 381.78 joules. Now let's backtrack here. I see 3 sig figs. I see 3 sig figs, 3 sig figs. I need to turn this into 3 sig figs. So I'm going to approximate Q to 3 sig figs for 382 joules. And that will be the best final answer I can provide. And I move on to the next. So 10 out of 10, pause the video, check yourself. Going. Gone. Let's get into it. So how many joules does it take to melt? Ooh, ring, ring. Uh-oh, I see a state change word here, or a phase change trigger. Let's remember that. How many joules does it take to melt 47 grams of ice to 0.0 degrees Celsius? Okay. Well, I got something different now. I've been told I'm trying to melt it. So I'm looking for the joules of a phase change. Okay. From what we just talked about, I'm talking about a phase change. So I got two options I can do. That one or that one. Let's see what I'm asked for. I'm asked for ice. So the phase change closest to ice, which is solid water, as I'm melting ice, is heat of fusion. So I'm melting. I want to use heat of fusion. Anything in this category right here, melting or freezing, you're going to be a heat of fusion value. And the heat of fusion for water is 334 joules per gram. Okay, so I know the Q is equal to mH sub F, or heat of fusion, because what I'm talking about is melting ice. Ooh, let me not scribble up my thing. Melting ice, and I know melting to be an indicator of a phase change. So I'm talking about the Q of phase change. I know I'm talking about Q because it asked me very directly how many joules. Joules is the measure of Q. Joules is the measure of Q. So plug and chug what we know. I have 47 grams of ice times 334 joules per gram. That gets me 15,698 what? Joules. But let's regroup here. I see 2 sig figs with that decimal. I see 2 sig figs with that decimal. And even if I gave only just that 0 right here, if I only gave this 0 or zeros anything to do with significance, no. So my default is 2 sig figs. So I count out 2 sig figs. I do some rounding. And I approximate Q to be about 1,600 joules. 16,000 joules. There we go. Easy, breezy, beautiful, straightforward. Try this one on your own. Pause the video. Do it. Pause it. Do it. Thank you kindly. Now let's get into it. I'm asked for how many joules does it take to boil. I am boiling 105 grams of water. I'm making some good pasta. But boil is a phase change trigger word, the exact same as melt. Boil triggers a phase change. What is stay? So that's a phase change. Boiling is a phase change. So I know I am going to have to do a phase change Q where I have two options. I have heat of vaporization, heat of fusion. But I'm asked for boiling, so if you recall on your phase change diagram, boiling is the act from moving from a liquid to a gas. So I'm boiling, which means I'm vaporizing because I'm using it with heat. I'm vaporizing. I'm going to use a heat of vaporization value. And the heat of vaporization of water is given to me in my reference sheet as 2,260. So since I know how many joules, I'm talking about Q of a phase change, I do 105 times that heat of vaporization constant we have equals, I'm gonna, let me pull it out here. 2373.00 joules. Good, beautiful, great, fantastic. Wrong number of sig figs. I see 3 sig figs, so my answer should be in 3 sig figs. So I see 1, 2, 3. Look at that one. La di da. Da da dee. 237,000 joules is the approximation of Q to the proper number of sig figs. And easy breezy, just like that. So hopefully things are starting to click. Now, let's make it spicy. So if you start with 35.0 grams of ice at -5 degrees Celsius and heat it until it becomes a liquid at 6 degrees Celsius, how much heat energy does it require? All right, so I know I'm dealing with a block of ice I have modeled here for you. That's 35.0 grams. And it's sitting at -5 degrees Celsius, which I know to be below freezing. It's below freezing. So I know it's ice. It's a solid cube of ice. And I heat it. So for me to heat it means my temperature's got to go up. So I'm moving my ice cube from a solid. I heat it some more. It hits my threshold. Now I've got to still ice, but now my ice is starting to separate. A little bit more, i.e. those ice particles I have that were once glued in space are now stretching apart because they have extra momentum due to the added heat. Because it told me I heated it, okay? So I started with ice and I heated it. So I'm putting energy into it until it's liquid. So I've melted it. From ice to when it's liquid is melting. That's the process I've gone through. I've gone through melting. Which means I have stretched the particles enough to where it's now no longer recognized as ice, but it moves into be a liquid state. It's a liquid state. Let me make that a little bit smaller. It's a liquid. And then I said I start with 35 grams of ice at -5 degrees and heat it until it's liquid at 6 degrees Celsius. So I've gone past the threshold of melting and I've kept heating it. So now I'm moving from just plain liquids to hot liquids. I'm adding in more energy, continuing to go up my ladder here. Eventually, I'll add so much energy, I'll move up here. That's the gaseous part. So now I'm starting to layer in some effects. So let's order what I just said. First things first, we had our ice. we had to heat it. So we're heating ice is step 1. We're heating ice is step 1. Then I have to what? I have to heat it so much till it starts to melt. Then I move from heating this till it starts to melt. So I move from this to this. Then I go up to this. I melt it down to a liquid because at 6 degrees, so I continue heating my liquid. So now I've gone from melting ice to actively melting. Now I'm working on heating my O2, H2O, excuse me. I'm heating the water. 3 distinct steps were mentioned to you. Now they've asked me for how much energy does it require to do this, to go from start to finish. So I'm talking about a summative Q value here. I'm talking about a summative Q value here. So I gotta find the Q of melting ice, heating ice, the Q of melting ice, and the Q of heating the water. 3 distinct steps I have to calculate information for. No big deal. Look, Mom, I can do some math. Step 1, heating ice. I know I'm heating ice. So heating anything, heating a substance, MCP delta T. I know melting, to melt is a phase change or a heat effusion factor. So I'm talking about Q equals MH sub F. Then I move back to heating my substance, which is heating water. So that's back to Q equals MC sub P delta T math. Then I plug and chug what I know. I'm going to start plugging in my mass of ice. So I'm going to look back at my problem and look for the mass of ice. Let me move this out the way for a second. Excuse me. All right. Heating ice. I have 35.0 grams of it. Ice. Ice probably has a unique specific heat factor. So let's scroll back over here. Bloop. And would you looky there. Indeed, ice does have a unique specific heat factor of 2.05 joules per gram degrees Celsius. Times that delta T value. Now let's talk about delta T. I start at -5 degrees Celsius. So -5 degrees Celsius is where I start at. I keep heating it until it's liquid. So I'm here, right? And I keep pushing up the track until I start to see it sweat. So here, I likely know that temperature for it to start to melt. This threshold is 0 degrees Celsius. So TF, that -5, is where I started. And as TI and TF is 0. So TF minus I'm going to keep that negative 5.0 in parentheses. You know what? Let me get myself some more working room. Why make it harder? We in the world of technological advances that let us be fancy. So let's be fancy. I ain't got to squeeze all that stuff in there. All right. Let me get right and actually write something we can see. So I got 35 grams of ice. And that specific heat of ice. And that delta T. TF minus TI. I know my TF is 0 because I heat it until it starts to melt. 0 minus where I started from, that negative 5. I'm going to keep that negative in parentheses, close everything out nice and neatly together, run my math. Zero minus negative 5 excuse me, I get Q equals 358.75 joules. Keep all your numbers until the very end. Keep all your numbers until the very end of this process. We always, always, always want to do significant figures at the very, very end, so that way we can use all of our decimals to help us out. Now, I move into my melting part, so that I did step 1. So now I've done this, so I'm moving up the ladder some more. I've done the melting gig. Now I've done the heating my ice enough to where it starts to melt, passing that melting point. So let's calculate how much energy it takes us to move from heating ice to melting ice. So let's talk about it. I have how much ice? 35 grams of it, times the heat of fusion. Heat of fusion I know to be a standard value on my reference sheet right here on the back with those thermodynamic constants. So now, run some math. Not those numbers. $11,690 joules. Let's keep it pushing. Now I'm moving from actively melting my water to heating my water to get it to this point right here, which is likely somewhere close to 100 degrees Celsius. So, but I told you stop at 6. So it's not all the way boiling yet. That would be somewhere over here. This would be my boiling point around 100 degrees Celsius. I told you I stopped at 6 degrees Celsius. So, do some math. I know my mass of the same water. I'm assuming I'm doing this in a nice, tight, contained vessel here where I can capture all of the things and my mass doesn't change. Now I'm moving from solid water to liquid water. 4.18. I'm heating liquid water because I told you it melts. That melting process is when we go from solid to liquid, from ice to liquid. That's why we're using 4.18 here. Then we get to TF minus TI. So to get here, we're talking about that 0 to -5 stuff. That's this. Now, let's talk about us moving from here to here. That would be what? TF. I told you where we stop at. Minus TI, where we initially began here. So I'm moving from -5 degrees Celsius to 0 degrees Celsius to 6 degrees Celsius. 6.0 minus 0. Run some math real quick. Ah. Hey. All right. 877.8 joules. Now, I can answer the question, how much energy does it require as a whole? How much energy, how much energy does it require as a whole? So we take this one plus this one plus that one. So you add all the found Q values for an overall effect. So I get something, let's pull it over here. I'm gonna just pull them out my calculator. 358.75 plus that 11,690 plus that 877.8 joules. That gives me a whopping overall Q of 12,926.55 joules. That's not good enough. I need to talk about sig figs. So in sig figs, I see 3 sig figs there, 2 sig figs there, 2 sig figs there. I'm gonna go with I need to be in 2 sig figs. So let's talk about the best answer to give me. We run it down to 2 sig figs. There's 1, there's 2. Let's influence that last one, that cutoff spot. 13, 1, 2, 3, 1, 2, 3 joules. 13,000 joules is how much heat energy it requires to move this block of ice, from here all the way to here. We good? Now do it again. Pause the video. Do it. I know it's rough. Thermochemistry can be rough, but you can do this. You got this. Pause the video and try it. Do it. All right, thank you very much. Let's get into it. So how much heat energy is required to raise the temperature of 5 grams of ice to 225 grams of water at 23.0 degrees Celsius to 45 degrees Celsius? All right. So let's kind of think about it abstractly. I likely got a cup of something. And inside that cup of something, I got a mass of water. So let's do a fancy doodle real quick, because it's always helpful to see it. I got some water. La-di-da, la-di-da. I'm a scientist, not an artist. I'm trying to make it party for y'all. All right. That's about as good as it's gonna get. Now I'm talking about, I got some ice. I want to see, and I probably, let's read it again. How much heat energy is required to raise the temperature of 5 grams of ice and 225 grams of water? So I'm going to assume this water is already hot because I'm talking about how much heat energy is required to raise the temperature. It's going from here to here. So I'm heating it some more. Okay. So my water is likely already at some kind of temperature. I have to start influencing my ice. Because you're only given information about ice and liquid water. You don't know much about the ice. So we jump to what we know the most about. I'm gonna try and melt the ice from the outside going in. I'm gonna try and mitigate my temperature going in here to in here to in here. I'm trying to see what's happening as I transfer some heat energy to my ice cubes. I'm gonna jump in to try and melt the ice. Because you don't know the TI, or the initial temperature of the ice, so you assume it's already in hot water and it's actively starting to melt. You lack the knowledge of its initial spot. Okay? So we're gonna start with melting ice because we know the TI of ice. So we're gonna melt the ice, and then we're gonna heat the water. So most of my energy will go towards melting my ice first, then heating the whole cup of water. So let's get into it. I know melting ice is a cue of a phase change, melting. That's heat of vaporization. Heat of fusion. That's heat of fusion. I have how much ice? 5 grams of ice. So I'm going to make that my mass value. Let's pull that in here. And I know the constant heat of fusion of water. What's that? So 5.0 times 334 gives me a whopping Q value of 1670. This is a scenario, how much heat energy is required to raise the temperature from ice in a cup from something to something. I'm talking about a situational Q value here. So I'm going to add up the Q. So this Q plus that Q equals the total Q. Capiche? So now let's talk about heating the water. How much water do I have? Well, if I've melted ice, wouldn't ice turn into liquid water? Ooh. So after melting ice, ice turns into liquid water. So that makes it 225 plus 5 equals a total mass of liquid water to be 230 grams of liquid water that we know about. Because I've already melted my ice. That's what I'm doing. Now I'm melting the whole cup. So instead of this, I'm talking about a new cup. With my ice already gone. Since it's already turned into liquids. I had 5 grams worth of ice that melted into my cup. Make that a little bit smaller here. And go forth and do some math. I know I'm heating a substance here. So that's Q equals MC sub P delta T. I've established my mass value right here as at 200. Oh, can't write. 230 times C sub P of liquid water, we should know by now, is 4.18 times TF minus TI. Where did I start? So I start of heating 5 grams of ice and 225 grams of water. I'm currently at 23. That will be an initial temperature. And I heat it till it hits 45.2. That'd be a final. So TF minus TI TF minus TI. Let me make that 0 a little better here. It's over here struggling. Trying to fit it all. There we go. And run some math. 230 times 4.18 times 45.2 minus... Mr. Cole forgot his parentheses. SpaghettiOs. That gives me a whopping Q value. There we go. So now I'm asked for a heat energy is required to raise the temperature of my situation here. So I'm going to take this Q value, and then I'm going to take this Q value, and I'm going to add them together. Nope. Can't look at that. There we go. So once we add them together, 1670 plus 213. Oh no, 343.08 gives me a whopping 23.23013.08 joules, because I've asked for heat energy, and I know heat energy is measured in joules. But how many sig figs? Always consider your sig figs. I see 2. I see 3. I see 3. I see 3. I see 3. Okay, how many sig figs should I have? The least number is 2. I'm gonna report in 2 sig figs. So we're gonna run this to 2 sig figs. There's 1, there's 2. So approximately your Q value is 23,000 joules of heat energy to get here. So that's how we go from here, where we started, to the end point here with no ice. So I've melted all the ice in my cup. I've left it sitting on the counter. It's now a watery mess. Capiche? On to the next. This part is where we're gonna start stretching your algebra skills. This is the algebraic way to think about specific heat in this part of thermochemistry, where I promise all you need to know is basic algebra skills. So let's walk through this one together before I make you try more. So I'm asked for, what is the specific heat? What is the specific heat? I know specific heat is a Cp value. And keep that in mind. I'm gonna change the color on that because I want to. That's a Cp value here is for specific heat of some sample of gold, which I don't even care too much about right now. If the temperature of, okay, that's a mass of a sample. That's a mass value there. Increases. Okay, so it's increasing. That's a verb. So it's changing. 8.2 degrees. That sounds like a delta T situation right there. When that much joules, 16.5 joules, joules is how we measure Q, all right, of heat is added. All right, I know I got a mass, I got a delta T, I'm looking for a specific heat. I'm probably heating a substance, and I know that because I'm given the substance, 18.21 grams of gold. So, start from the top. You eat an elephant or eat a big meal, one bite at a time. Start off with what you need to know. This is my roadmap. My formula is as such. I'm given a Q value here. I'm given a Q value here. I'm going to write it in. I'm going to substitute Q for 16.5 equals, I have a mass value. I'm going to bring it down, 18.21 grams. And it says, what is the specific heat? I'm going to call the specific heat X, just so I can simplify what I'm looking for here. And we're familiar with how to find X in a problem, so let's flex those skills. Now I'm talking about delta T. Delta T is my change in temperature, and I know it increased 8.2, so 8.2 is my delta T. All you gotta do is find X. So you can do it one of two ways. You can combine like terms, or you can do it stepwise. Let's go ahead and combine like terms here. I see a constant value with this one and this one. Those are numbers without variables, so I'm going to run them together. 18.21, I'm multiplying here, so 18.21 times 8.2. That gives me a whopping common factor of 149.322. Notice how I did not cut off any of my decimals. I'm keeping all my numbers while I'm doing math. I'm keeping all my numbers while I'm doing math. Now, how do I isolate that X? I know I gotta do the opposite of multiplication. that be division. And what you do to one side, you must do to the other. That goes bye-bye, because something over itself is 1. Now I got 16.5 divided by, I'm going to recall my answer down here to save me some calculator entries. And I have 0.1104994575 equals my X, which is specific heat. So officially, you're talking about joules per gram degree Celsius, but let's look at my problem one more again. I'm talking about a final answer, so I gotta consider some sig figs. I see 4 sig figs, I see 2 sig figs, and I see 3 sig figs. So I'm gonna go with the least number possible. I'm gonna do 2 sig figs. So this number to 2 sig figs is 1, 2. That 0 doesn't do jack diddly to that 1. So your Cp value is approximately 0.11 joules per gram degree Celsius. That, my friends, is how you find those. Or if you want to do it the other way, where you just take each individual factor and move it individually, you will get the same exact answer, because math is math, and you will run the exact same problem and come to the same conclusion. And a fun way to check it is to use your reference sheet to your advantage. I'm talking about a sample of gold. So if I pull my reference sheet out, and let's just see what it has to offer us, I see with my little eye some standard values here. I see with my little eye some standard values. This standard value would be gold. Its specific heat is given to me as a constant lab value, which is wonderful. I should be somewhere close to what's established as a constant value. And we can agree that 0.129 is pretty flipping close to what I've calculated here. Is it exact? No, because this is a different scenario in a lab with likely not a pure sample of gold. But it's pretty close, so I know it's mostly gold, and it's on point with my answer I would expect. So that's it. That's all. That's how you run this half of thermochemistry. I am always here for questions. You can shoot me an email. I am here to help where I can. Until the next time.